Pirates. Welcome to week 2 of the Learning on the Edge summer program, What Would Steve Do? I'm showing you right here a pirate flag to remind you that I'm going to call you guys pirates. And you know, last week I asked a question during attendance, why was I calling you pirates? There was a couple of reasons. One, because you're all different grades, so I can't just call you 5th graders. And the second one, more importantly, which most of you understood, is that Steve thought differently and you guys think differently. And I think that's super cool. That's why I chose you guys for this summer program. So you're my pirates. So today what you're going to be learning about is Newton's laws of motion. We're also going to introduce you to the 2 prizes this week. There's 2 prizes and you get to see those during this video. So let's take a look and get you started with an introduction to Newton's laws of motion. Okay, let me just find it. Here we go.
Sliding on the ice will keep on going.
All right, here we go.
Newton built on the work of Galileo and Kepler and came to the conclusion that the motion of falling bodies, the movement of planets, and in fact the movement of any object at any time was due to being acted upon by a force, a push or a pull. He worked out what he called the 3 laws of motion, which govern the movement of all objects at all times and in all circumstances. The first law states that an object's natural tendency is to continue what it is doing. If it is moving in a straight line at a constant speed, it will continue in a straight line unless acted upon by another force. It also states that an object at rest will remain at rest unless a force moves it. This is known as the principle of inertia. There are many examples of the first law. The space probe Pioneer 10 has been drifting through space for 35 years. A hockey puck sliding on the ice will keep on going. And this steel pipe won't move until the claw does its job.
Minus 10 seconds. 9, 8, 7. Go from 8 engine start. 6, 5, 4.
An object's mass is a measure of its inertia. The greater the mass of an object, like the shuttle, the harder it is to move it or change its direction. Note that physicists use the term mass, or the total quantity of its matter, rather than weight, because in space, all objects are weightless, but they never lose their mass. The second law describes how an object accelerates or changes direction when a force is applied to it. The change depends on the magnitude of the net force. The second law also states that the acceleration due to a given force is always in the direction of the force. The mass of the object is also important. The larger the mass, the greater the force needed to make it accelerate or change direction. The second law can be written as F equals ma. This formula is saying that applied force, or F, equals mass times acceleration, ma. This formula is used to describe the motion of objects under all kinds of circumstances. If a ball is thrown horizontally, it will continue forever unless a force acts on it. The Earth's gravity is a force that pulls on the ball and it falls to Earth in the direction it is traveling. Newton's third law of motion deals with interacting forces. It states that for every action, there is an equal and opposite reaction. The opposing forces of these two tug-of-war teams balance each other, The swimmer pushes off from the floating raft, propelling his body away from the raft, but also pushing the raft backwards. As the law states, for every action, there is an equal and opposite reaction. A book sitting on a table remains where it sits because the table pushes back with a force equal to the book's weight. This seems like a simple-minded idea, but an architect or engineer designing a building had better understand the third law of motion and ensure there is enough support to carry the weight, or the building will fall down. In the building of bridges, or any complicated structure where weight must be distributed, the calculation of net force is vital because it shows where the stress will be concentrated. This is calculated through vector analysis.
Okay, physics can get really hard really quick, but those are Newton's 3 laws just in general. Now, if you're a 5th grader, or ever been a 5th grader in my class, you will know that one of the things I do to introduce coding and game design is we play a game called Portal. And I had a friend a couple years back that made us a Portal video using the game Portal to teach us Newton's law of motion. I want to show you that. It's a pretty cool video.
Back on the cube. Let's go ahead and take a look. Alright, good morning everybody. I'm excited to be back with another installment of Physics with Portals. It's been a while and today's demonstration is going to be all about Newton's 3 laws of motion. This video goes out to Nathan Manderfield, a 4th grade teacher in Bermuda Dunes, California, whose students will soon be learning.
That was back when I taught 4th grade. That's when they made me this video. So he didn't mess up. That's when I taught 4th grade.
All about Newton's laws. Let's go ahead and get started with Newton's first law. Newton's first law basically says that objects that are moving will keep moving, and objects that are sitting still will keep sitting still until some type of action or some type of outside force happens. This may sound kind of complex, but it's actually something that's very, very simple. We can see an example of it right in front of us. This cube that's sitting still is sitting still, and we don't expect it to all of a sudden start moving for no reason. There's got to be a reason that it starts moving, and that is an example of Newton's first law. We can be that reason. Let's go ahead and bump it. So we walk up against the cube, we bump it, and the cube starts sliding. That cube would never have started sliding, its motion never would have changed until something happened to it, and we just happened to be that something that happened to it. Alright, let's look at another example. We can see a cube sitting up here in this cube dropper high above the ground. That cube sitting still is going to keep sitting still until something happens to it. In this case, that something is going to be gravity. We're going to press a button, the cube dropper is going to open, and the cube is going to start falling. That, of course, seems pretty obvious, but let's think about that a little bit deeper. Why does the cube start moving? There's got to be a reason. In this case, the reason is gravity. Gravity is pulling the cube towards the ground. Okay, so let's go ahead and see that in action. I'm going to drop back down here, press the button, and we can see the cube fall, and then slide across the floor. So there are at least 2 examples of Newton's first law here. The cube falling is an example of an outside force acting on the cube to cause it to start moving, and we can see the cube sliding along the floor. As the cube's sliding, it's not getting any faster or slower, and it's not changing direction. That's an example of Newton's first law. It's an object in motion, and it's staying in motion. It's keeping its same motion until something else happens to it. In this case, that something else is the force of gravity pulling the cube into the pit. Very, very cool. Okay, let's jump ahead to Newton's third law. We're skipping the second one for now, but don't worry, we'll come back to it. Newton's third law says that every action has an equal and opposite reaction. This is used in rockets, it's used all over in physics, and today we're going to see an example of it when we launch this cube against a wall. So we have a cube dropper, we have an aerial faith plate, and we have a wall. We're going to press this button to our left, the cube is going to fall, it's going to hit the aerial faith plate and then bounce off the wall. Let's pay attention to that bouncing action, that cube hitting the wall and then bouncing backwards. In this case, the action is the cube hitting the wall, pushing on the wall, but the wall also pushes back on the cube. It has to, according to Newton's third law. There's got to be a reaction. So the action is hitting the wall, the reaction is the cube flying backwards because the wall pushed back on the cube. Let's go ahead and take a look. So we press the button, cube drops, hits the wall, and then bounces backwards. It doesn't bounce back that far, and there can be other factors that determine how far back it bounces, but nevertheless, it did bounce back, and that is all because the wall pushed back on the cube. If the wall didn't, the cube would have gone right through the wall. Very cool. Alright, let's go to Newton's second law. Alright, Newton's second law, which we're doing now, is a little bit more mathematical in nature. Newton's second law says that force is proportional to mass and acceleration, or F equals ma. M is of course mass, A is acceleration, and F is force. This gives us some math to work with so we can start calculating forces. In front of us now we have orange gel, or propulsion gel. Propulsion gel causes us to run faster than we normally would. Now when we run, our legs are actually our force. Our legs are the outside action. We push down on the ground pushes back on us, and that's Newton's third law in action. We can calculate that force. So let's go ahead and start running. You can see we get faster and faster, and we launch ourselves up onto this ledge. Okay, so let's see if we can figure out how much force was applied to us, or how much force had to happen to us in order to accelerate us to the right velocity to hop up onto this ledge. So we know that force is equal to mass times acceleration. Our mass, according to the game, is 85 kilograms. And I did this before, and I'll be happy to explain in the comments. Our acceleration from the propulsion gel is 12 meters per second squared. Multiplying the two together, we get 1,020 newtons. That's right, the unit of force is a newton, and that's not an accident. Newton is all about forces, so of course forces are all about newtons. Okay, very cool, very fun, and these are just a few simple ways of showing Newton's laws within the world of Portal 2. There are many, many, many more examples because Newton's laws literally govern how everything moves.
All right, that's kind of cool to see it. Now let's see it applied and an introduction to your prizes for the week. Jalen and her friend helped with this part. So first, let's take a look at Newton's, let's look at which one should we do first. Let's do this one, Newton's first law. Wait, let's see that again. Newton's okay. Now the prize giveaway. We're going to take a look at what prizes you're going to get this week.
So this is a version of one of your prizes for the week. Yours isn't quite like this, but it's a slingshot one. So remember, learn about Newton's laws of motion. For every action, there's an equal and opposite reaction. So we have a water balloon. If we pull it only back this far, we let it go, that's how far it goes. Okay? But Newton's third law says for every action, hold it up boys, higher. For every action, there's an equal and opposite reaction. So if we go, okay, that one was that big fail. It's all right. Let's watch one more, two more. Yeah. For every action, there's an opposite and equal reaction. Watch. Boom! Okay, one more. And let's see if we can shoot one over the house. Go, get up in the air, boys.
Shoot.
Oh, epic. All right, okay. Well, all right, so now, this is the house. We're going to see if we can shoot it over the house. Okay, so here we go. Cut her down. Oh! Over the house! Boom!
Okay, one more.
Okay, one more.
Okay.
See, now we got to film the backyard at the same time and try to hit somebody. I go, yeah, aim it a little bit more this way, Jason. There you go. Okay, ready? Over the house. Okay.
All right, that was pretty cool. So one of your prizes is going to be some water balloons and a slingshot. The second prize I'll show you towards the end. So I have one more video to show you, and that is how physics can be applied in a football game. And it's a pretty cool video because it also shows you the math and how complicated the math can get in physics. Okay, check out this.
Deep for Decker. What a grab! Touchdown, Minnesota!
Looks like that hit on Golden Gopher wide receiver Eric Decker didn't feel too good.
Decker's shaken up as he got hammered.
The blast from Cal safety Sean Cattouse had enough force to cut Decker's jaw open. And while Decker clearly was uncomfortable after the hit, the Gopher Athletics staff was able to stitch him up so he could head back into the game, which is amazing considering the force his body withstood.
Just to hold on to that ball is a testament to the hand strength of Eric Decker.
But hold on a minute. Just how much force did Decker endure?
How hard was that hit? How many G's did Decker experience during that hit?
To find that answer, we took University of Minnesota physics professor Dan Dahlberg out to the TCF Bank Stadium field to break down the science behind Decker's amazing touchdown catch.
Knowing the time and the distance where he landed, I can now calculate what that velocity was.
To find those numbers, Dahlberg first had to study some film. Using the game footage, he was able to break down the play in several different ways, coming up with estimated speeds of Decker, Cattouse, the impact, and the time it took for both players to land. Next comes the math.
And so that acceleration that he was experiencing
Look at that math problem. That's a physics problem.
was 345 feet per second squared.
Knowing factors like Decker's speed in the 40-yard dash and the time it took for him to travel between the 10 and 5-yard lines, which was determined by watching the video, Dahlberg was able to come up with an equation that allowed him to estimate the amount of G-force exerted on Decker's body during the brief impact. And the key to doing that was determining the distance between where Decker was hit to where he landed on the ground.
So in terms of G's, I'm going to take this 345 feet per second squared and divide that by the acceleration due to gravity, which is 32 feet per second squared. And when we do this, we find that his acceleration was 10.7 G's.
To be precise, Dahlberg said Decker felt 10.78 G's of force during the hit. Now that 345 feet per second squared divided by 32 feet per second squared, which is the force of 1 G, gravity, and that's how you get 10.78. 10.78 G's of force that Decker suddenly felt during that hit.
Now, that's a pretty big number. I found one report online where Navy carrier pilots undergo acceleration of about 3 G's when they're taking off from the catapult assist on the flight. In car wrecks, it looks like you could have as much as 40 G's. To give you some idea, this 10.7 G's meant if Decker weighs, say, 200 pounds, right at that point, during that collision, he's weighing more than a ton.
Standing on the field with no other forces factored in, Eric Decker weighs 220 pounds. For a brief moment during the impact, Decker had 10.78 G's thrusting him. 10.78 times 220 is more than 2,300, which means for that brief impact, Decker felt like he weighed 2,300 pounds. That's more than 3.5 times the force Navy pilots feel when they're being catapulted off an aircraft carrier's deck. And yeah.
Following the review, the ruling on the field, the touchdown has been confirmed.
Decker held on for the touchdown.
That's pretty cool. Okay, last thing we're going to do for this is break out the camera and show you the last prize. So if I go over to here, look at our prizes are growing. Our prizes are growing. So there's one of the prizes for the week. Boom. And the other one is going to be that one because of Newton's third law of motion. So we'll have 2 winners. And the only animal I can show you is right here this morning. And that is Mr. Nippers. Say hi, Nippers. Meow. He was sleeping. All right, pirates. See you guys on Thursday.